Hello everyone, welcome back. I am Sheila CS, pursuing PhD in the Network Research Lab under the supervision of Professor Joy Curie in the Department of Electronic Systems Engineering, IISc Bangalore. So before going to the next experiment, let me review what we did in the experiment number 1 and 2. Experiment 1 titled IEEE WLAN 802.11ax channel model. Here we basically obtained the channel impulse response for model D delay profile and the statistical distribution of channel amplitude or envelope, HI. Basically, we discussed here what a multipath propagation is, and also I discussed 6 WLAN indoor channel models defined by the standard, and the path loss model is also discussed, and finally at the end I obtained the statistical distribution of channel feeding coefficient. In experiment number 2, channel frequency response of indoor channel models. Here, we basically obtained the channel frequency response, magnitude HI using HELTF field of the packet preamble, and the statistical distribution of channel gain, magnitude HI squared. Also, we compared the channel gain, that is magnitude HI squared, for different indoor channel models, that is channel model B, D, and E. Today, let's discuss the experiment 3, that is IEEE WLAN 802.11ax5 frame format. The learning objectives, initially we'll discuss what some of the features of IEEE 802.11ax, then HTTPDU frame format. We'll see what is the legacy part of the packet preamble and the HESIG field in particular. And at the end, I'll plot the preamble of the 11ax and in particular discuss more on LLTF portion of the packet preamble. 802.11ax file is also called as high efficiency file. So it is the operating band or 2.4 gigahertz and 5 gigahertz. 11AC supported only 5 gigahertz operating band, but not 2.4 gigahertz. The extended recently Wi-Fi 6 is extended to 6 gigahertz and it is called as Wi-Fi 6E. And one must note that this 6 gigahertz operation is not supported by all countries. Only specific countries support 6 gigahertz operation, and a separate certification happens for that particular band. The data rate support is 8.6 to 1201 Mbps per special stream. The modulation is same as 802.11 AC, but 11AX in addition supports 1024 QAM. The coding is same as 11AC. It supports both BCC and LDPC. The bandwidth is 20 megahertz, 40 megahertz, 80 megahertz, and 160 megahertz support, similar to 11AC. In 11AX, the OFDM symbol duration is quadrupled. In 11AC, it was 3.2 microseconds, but in 11AX, it is 12.8 microseconds, and also the number of subcarriers is also quadrupled. So effectively, the data rate remains the same because the number of subcarriers are increased, but the time, the symbol time duration is also increased by the same amount. Why is this done is to support some of the features which is required for OFDM-A, that is multiple access, orthogonal division, orthogonal frequency division multiple access. For the first time, it is introduced in 11AX. So increase in symbol duration and the number of carriers resulted in increase in spectrum efficiency. So we know IEEE 802.11 is a packet-based protocol. So each PPDU contains preamble and data fields. PPDU is physical layer protocol data unit. So 11AX supports 4 different types of PPDU. The first one and the most, which is mostly used in practice, is HE single user, high efficiency single user PPDU. HE extended range single user PPDU, HE multi-user PPDU, HE trigger based PPDU. So HE SU PPDU is used for single user transmission. This extended range SU PPDU is used for extended range, as the name indicates. It is used to get the longer coverage. So here the standard supports it, but it is not practically used because no chipset supports this mode of PPDU. And in multi-user operation, that is MU OFDMA and MU MIMO, downlink transmission, MU PPDU, HEMU PPDU frame format is used. And for uplink MU transmission, both for MU OFDMA and for MU MIMO, HE trigger based PPDU is used. So when we see all these four frame formats, one thing to notice is the first three fields, that is LSTF, LLTF, and LSIG, are present in all PPDUs, and it is also present in the legacy PPDU formats. This is to support the backward compatibility. So LSTF is basically used for packet detection and synchronization. The LLTF is used for channel estimation and decode the pre-HELTF fields. That is whatever the portion of the packet preamble before HELTF is called the pre-HELTF. So LLTF is used for channel estimation and to decode the pre-HELTF fields in order to recover the information. Then LSIG field has the length of the packet in microseconds. So the RLSIG field here is the repeated LSIG field. It is used to distinguish between the 11AC and 11EX PPDU. The LSIG and RLSIG also has the extra 4 subcarriers on which the channel can be estimated. So the LLTF channel estimates are updated in order to create the full channel estimate. So next comes the extended range SUPPDU. As I told, it is used to obtain the longer coverage, and this, when you compare with the other PPDU formats, it has longer HECK, which is of 16 microseconds, but in other PPDUs it is 8 microseconds. And also some fields here are boosted in power in order to get the longer coverage. The next is the HEMU PPDU, which is used for downlink multi-user transmission, both for MU FDMA and MU MIMO. So the unknown parameters of HEMU packet are obtained after decoding the bits in LSIG, HESIG-A, and HESIG-B. The HESIG-A has common transmission parameters of HEMU packets such as data rate, MCS, etc. The HESIG-B also has common field and the user specific field. So this will specify who are the intended receivers for this MU frame which is being transmitted, and the user specific field will have the RU allocation information and the transmission parameters. And if you notice, this HESIG-B field is present only in the HEMU PPDU. The other PPDU do not have this HESIG-B field. Then there is HESTF and HELTF, that is a short training and long training field, which is used for, again, channel estimation. This LLTF is used at the beginning of the packet to estimate the channel. Here, this HELTF field is also present in between, just before the data PSDU. There is HELTF, which is used for channel estimation, and it is of variable length, which varies depending upon the scenario. The last is the HETP PPDU, which is used for uplink trigger-based uplink MU MIMO or MU OFDMA. In this has all HESIG-B is not present here, as I told, but otherwise almost all the fields of HETPU is similar to this HEMU PPDU. Then comes this PE, the packet extension. This helps certain devices to prepare the response frame. That is, some devices need more time to prepare the response frame. So basically, it's a dummy field in order to fill up the time. So this completes the PPDU format. So we'll next see more on HESIG. So OFDM symbol duration field before HELTF, that is this LSTF to HESTF, the OFDM symbol duration here, it is 3.2 microseconds. But in HELTF and HE data, the OFDM symbol duration is quadruple, that is 12.8 microseconds for HELTF and PSDU. The HESIG-B has variable number of OFDM symbols, and it is sent just before HELTFs. It includes MCS information for each station, and HESIG-B, as I told, it has a common field and user specific field. And then there is something called GI and LTF size. GI stands for guard interval, and LTF size is the size of HELTF, which is also called as midumbil. And this is specified in HESIG-A field. So this HELTFs are also called as midumbils. So it is variable in size 1 to 8. So the size of HELTF and the guard interval is specified in HEC gay field. So these are the HEGI and LTF options which is available in 11AX. So there are 4 combinations, and for HESU you can see all 3 guard intervals is supported or it's specified by standard. 0.8 microseconds, 1.6 microseconds and 3.2 microseconds. When it is 0, it is 0.8 microseconds with 1x LTF. When I say it is 3, it is 3.2 microseconds with 4x LTF for HESU. So mostly GI in HESU is 0.8 microseconds because this 1.6 micro or 3.2 micro is basically used for outdoor communication scenario. And in HETB, the support is 1.6 and 3.2 microseconds GI, and mostly 3.2 microseconds is used. And LTF support is 1x, 2x, 4x. So it supports all 3 kinds of HELTF. Here also it supports all 3. But when you go for HEMU, there is all 3 guard interval length is supported. But HELTF, if you see, it is longer. It is 2x, either 2x or 4x in case of HELTF. So what is the benefit of using longer HELTF? It basically helps the receiver in order to estimate the channel accurately. I think now we can go to the MATLAB code. Yeah, this is a simple experiment which is where we can learn more on the different fields of the packet preamble and see how the preamble portion looks like, and we'll see how LLTF, specifically LLTF, how it looks by plotting the waveform. So initially I'm generating HESU configuration object. The bandwidth of operation is 20 megahertz, and PPSK modulation with coding rate half is supported. HELTF type is 1. The guard interval is 0.8 microsecond. So in this, if you recall this, I'm using HESU, guard interval is set to 0.8 and HELTF is 1x. So the combination 0 that I'm using, and data field is 100 bytes. The PSDU, I'm creating a PSDU by generating a random bit pattern, and then PSDU is passed to the WLAN waveform generator in order to produce a 11AX multi-user waveform, single user waveform for HE single user packet. And here I'm configuring a TGX channel with 20 megahertz bandwidth, and carrier frequency is 2.4 gigahertz. Default it is 5.25 gig, and the path gains output is set to true. The channel model delay profile is chosen as model B, where we have 9 non-zero tabs, and the last scale fading effect is enabled, and it is path loss is enabled. The TXRX distance is set to 10 meters. We are in NLOS propagation because the breakpoint distance for model B is 5 meters. Here we can get the information of the TGX channel. You can see there are 9 path delays, and path loss is 64.56 dB. So then this waveform is passed through a TGX channel. So here we have set the properties for TGX channel. Once I pass, I get the path gains and TGX output. This path gains can be used to obtain or plot the impulse response of the channel. So now I just take the TGX output, and I'll take the input TX waveform, which was fed into the fading channel. Initially, first I'm going to sketch the waveform, that is a TX waveform, which was given as input to the fading 11x channel, and the waveform which has come out of the fading 11x channel. So this is the first figure. So simply this is the input to the channel, and this is output to the channel. So this waveform has some initial initial part of this waveform is a preamble portion. We also have data portion because I have set data size to 100 bytes. If you make it 0, whatever you get will be simply preamble without data. So now this has preamble plus data, which is almost 150 microseconds in length. So next is I'm going to extract only the preamble portion. So in order to do that, I'm going to make use of this WLAN field indices. So HIND has the index values or pointers to different fields of the HESU packet. So you have LSTF. First 160 samples corresponds to LSTF. Then next 160 corresponds to LLTF. The next samples corresponds to LC. So this all three put together, it is the legacy part of the packet preamble. Okay, this is around 400 samples, and it accounts and this will be equal to 20 microseconds in length. So how to calculate the time duration? Here, basically, when you see the sample rate in the code, SR, yeah, this is the sample rate. It is 20 megabits per samples. So when you have 20 megabits per sample, what is the time duration for 160 samples? So it is nothing but 4 microseconds, right? Sorry, it is 8 microseconds. Okay. So similarly for next 160 samples, again it is 8 microseconds. 80 samples, it is simply 4 microseconds. So 8 plus 4, you have 20 microseconds preamble. So when I tell, this is the legacy part of the preamble. When I tell preamble, it is all these from LSTF to HALTF. Okay, then we have 800 samples. So if the sampling rate is 20 megabits per sample, then if the sampling rate is 20 megabits, 20 mega samples per second, then what is the time duration? It is for 800 samples. What is the time duration? We have 40 microseconds. Let's see. Yeah, you have 40 microseconds. So SR is a sampling rate, and the unit of the SR, the sampling rate, is samples per second. So 800 samples account for 40 microseconds. Then with HE data, it's more time. I think it is around 150 microseconds. It's around 150 microseconds. So I'm just extracting the 40 microseconds preamble portion, leaving the HE data. Okay. So that is what is done in the next part of the code. So first I've sketched input output, then making use of this indices. I'm simply extracting the first sample of LSTF to the last sample of HALTF. So this preamble will have 800 complex samples. So I'm going to simply sketch that, which will have the duration of this is 40 microseconds. So now again within this I'm going to extract only LLTF. So in LLTF, all LLTF, the 161 to 320 samples are extracted. So this has 160 samples, right? So what is the duration of this? It is simply 8 microseconds. But just to, I want to emphasize something here. So I am here, earlier the x-axis was time, but now x-axis is sample number. So what I have done is, if you see in the second plot, let me divide this one for easy explanation. Let me divide this 160 samples into first 32 samples, then next 64 samples, 64 samples. So the 64 plus 32 is nothing but 160, right? So the sample number 33 to 96 and sample number 97 to 160, they are identical. So this portion is repeated, right? That is one point. Second point is the last 32 samples of the repeated portion is again repeated and it is prefixed in the beginning. Okay, so this red thing, whatever I have done, it is copied to the first 32 samples. So I repeat, the 33rd sample to 96 sample is copied and it is repeated 97 to 160. So the pink portion and the green portions are identical. And again, the last 32 samples, okay, that is from 129 to 160 sample, it is copied and it is put at the beginning. So that is known because it is standard specified, right? So just to verify that fact, I have extracted those samples and I'm trying to sketch with a different color to just verify that fact. So this is LLTF portion or HL, LSTF, RLC, everything is specified by the standard. And here we are simply verifying the fact to make sure or to see like how exactly that is being happened. I think that is all in the code. So to summarize what we did, this is simple experiment just to know the different field of the packet, different PPDU formats supported by 11AX and the different fields within the packet, right? And as I told you, most of the time it is HESU PPDU transmission that happens, and this is rarely happens in practice because no chipsets supports it. And these are the different GI and LTF options. So these combinations are available. So that is all for this particular experiment. Thank you.